Hello, everyone, and welcome to another wonderful day of physical chemistry. So today we're going to expand on our previous knowledge of rotational spectroscopy to introduce Raman spectroscopy. So just as a quick overview of what is involved in rotational Raman spectra, essentially what we're going to be doing is taking a pre-existing rotational state with a given level J. Then we're going to hit it with very high energy radiation, often in the electronic excitation region. So we're doing an electronically coupled rotational spectra. And then what we're doing is going to be analyzing the wavelengths of light that come off. So theoretically, this system should end up relaxing either back down to its pre-existing J state to generate Rayleigh scattering, a higher energy J state to generate Stokes scattering, or a lower energy J state to generate anti-Stokes. So one of the biggest things that's involved with rotational spectra is that rotational spectra involves a two-photon event. First, an absorption and an emission event. And because that absorption, both of these events are rotational and electronic in nature, one of the biggest things that's unique about Raman spectra versus rotational absorption spectra is that we're going to have a different set of selection rules. So first of all, we're going to start by looking at the gross selection rule. So for absorption spectra, rotational absorption rotational absorption is only allowed for a polar molecule. However, for Raman spectra, all that we require is the molecule be anisotropically polarizable. Now, this is a big, complex word, but essentially what it means is when I expose the system to an electric field, it should have a distortion of its electron density in a single direction. So essentially what it is telling us is that I apply a electric field, I generate a dipole. We most commonly know this as a polarizable system. Think about things with induced dipole. If you can do that, you're generally anisotropically polarizable. So biggest benefit of this for us is it means that if I have a linear molecule or a symmetrical molecule that's nonpolar, it can still be categorized as Raman active, or essentially it can absorb via Raman spectroscopy, even if it may be microwave inactive, which is another way of saying I can't see it using typical rotational microwave spectroscopy. However, one of the big things about anisotropy is that it really is telling us the system doesn't distort evenly in all directions. Now, the notorious case of a system that will distort evenly is going to be spherical molecules. So if I'm a spherical molecule, which by definition will all be nonpolar, you're still going to be rendered Raman inactive. So if you're trying to do rotational spectra of methane, best of luck. However, we do have a large number of molecules such as CO2 and iodine that quickly have now been rendered Raman active, so I can actually figure out their rotational spectra. However, we still need a set of specific selection rules. So a good way of analyzing the specific selection rules for Raman is the fact that, again, it's going to be a two photon event. And each one of these is going to have a possible rotational transition of plus or minus J. So when I go excited up electronically, I could have a rotational relaxation or rotational excitation, but the J has to change. However, when I then emit the subsequent photon, the same rules apply. So I could have a plus one, minus one, which would then bring me back to the same place. So what we're going to find is these three classes of peaks depending on how these two rotational transitions couple. So for Rayleigh scattering, I'll have an example like that: increase and then decrease in rotational levels, or decrease then increase. So essentially I've got one of each, and they cancel out, and I get my traditional Rayleigh scattering and really no change in the uh, rotational state. However, we also have Stokes, where where under each transition event, I will increase the rotational level for a net of +2. And then anti-Stokes, where each rotational event, I'll have a -1 transition, and I'll go down 2. So we're going to go ahead and examine each one of these three cases kind of individually. So Rayleigh scattering, so this is the case where I have a different transition each time, brings me back to the same rotational level. Well, this really helps illustrate what one of the big differences of Raman versus traditional spectroscopy is. Because in Raman, I'm inserting a photon of given wave number of with a initial wave number. And when I have Rayleigh scattering, I get that same exact frequency back out. So frequency in is frequency out. These two wavelengths are identical. And as a consequence, we have a single line, because it doesn't matter what my J state is, I'm always going to generate this same peak. So I'll have a single Rayleigh line, which essentially can be thought of as a way to tell what your incident radiation is. It's a good confirmation point. And I'll get this guy back. And because every system can do this, this is definitely going to be a very intense line. However, it contains very little information besides confirmation of what your incident radiation is, which can be used for the analysis of your Stokes and anti-Stokes lines. So next up, we'll do the Stokes line. So Stokes line, I'm going to be increasing in energy level by 2, which means that I should have a wavelength that occurs at a slightly lower frequency than the additional Rayleigh peak, because I have less energy coming out than I put in. And we can essentially analyze this numerically, where I should end up having my initial peak minus this correction of the difference in between my starting state and my excited state. So using our previous knowledge of Rot vibe spectra, we should be familiar with this general idea. And what we generate is a line based on the initial incident wavelength, and then minus twice the rotational constant times 2j plus 3. So again, all of these peaks are going to be located at lower frequencies, and worth noting, should all have a consistent line separation. So again, just like absorption events, an even line separation between peaks. However, note that this is going to be shifted. For absorption, the separation was twice the rotational constant. For Stokes lines, this is going to be 4 times the rotational constant. And again, similar to absorption events, we're going to have a highest peak intensity for J values that are most commonly occupied. So again, at these intermediate J values. However, we can also do the same analysis while looking at the anti-Stokes lines. So now I'm decreasing J levels as I go from J to J minus 2. So I should have a slightly higher energy. And again, we can do the same idea by subtracting out the difference, which should be negative, of my initial state and my ending state. So what I end up having is a vibration, my Raman peak should occur centered again on my initial incident wavelength, wave number, plus essentially at a higher frequency of twice our rotational constant times 2j minus 1. So these will be a little bit closer to the Rayleigh line than the Stokes peaks. But again, it is worth noting that they will, and again, they're going to be at a higher frequency, because again, there's more energy out of this system. And it is worth noting, though, that they are going to have the same exact line separation as our Stokes peaks of 4 times the rotational constant. Because again, we're still going from 0 to 2. However, when we we can use our Stokes and anti-Stokes lines together, just like we did for absorption spectra, to determine the moment of inertia and the bond distance for spectra that are microwave silent. So again, very useful for a lot of nonpolar species. However, it is worth noting that when I go to symmetric species instead of spherical or linear, we have a slightly different set of selection rules. And one way to think about this is these selection rules are going to become slightly relaxed for a symmetric rotor as I have more possible rotations. So for a symmetric rotor, while like absorption spectra, I still can't have excitations in the perpendicular regions because in this case, we have we have no anisotropy in that direction. So essentially, since this direction is even, I can't induce any movement in that direction. However, we do see the emergence of a new set of peaks. As my J value isn't forced to change by 2s, but can also change by 1s. So we can have peaks at 0, +1, -1, and +2, -2. So the biggest consequence of this is it's going to greatly complicate analysis of the Stokes or anti-Stokes regions, as for the Stokes region, we can have +1 and +2 transitions overlapping each other, which does, again, make it so you need to be much more careful for Raman analysis when dealing with symmetric molecules. So next time, we're going to go ahead and start with a quick recap of vibrational spectroscopy. Until next time, take care.